Thanks, Joe. Thanks, Jose. It's great pleasure to be to present in IIFC webinar series. I think that's the second one in 2025, and that's a true honor. Um, so uh, I just start with some basics about us from where we're coming from. Probably some of you know Sydney, that's part of Australia, and that's in state of New South Wales. We basically in eastern part of Australia, and you might know and be familiar with these structures because we are mostly structural engineers, Sydney Opera House and Harbour Bridge. We, if you are familiar with our animals, we have very cute animals, kangaroos, koalas, and very uh, friendly faces, but also we also have very scary ones, basically deadliest spiders in the world. So uh, different types of animals and uh, friends we have here. Uh, in terms of introduction to our university, University of Sydney is the first university in Australia, and that's established in 1850, and roughly around 1850. And as I said, that's around 150, 170 years old. Uh, we have international students, diverse international students, and then we offering different PhD degrees, undergraduate degrees, and so on. Um, A School of Civil Engineering is one of the oldest schools in University of Sydney, and we have different research teams and groups that we focus on materials, transport, structural engineering, humanitarian, water, and so on. And I think similar to other universities, we have a state-of-the-art facilities for material testing, characterization, and structural testing. So to give you a better understanding about my research area, it's basically in intersection of materials and structures. I focus a lot on material side, but the application would be in structural applications. Majority of my research is related to sustainability and circular economy, specifically composite waste, and looking at low carbon concrete, low carbon construction, and specifically concrete cementitious materials, and looking at self-sensing in cementitious materials, and also structural health monitoring using those self-sensing techniques, and looking at how we can prevent corrosion and improve the durability of structures. Most of these, the common area of focus is basically carbon fiber and carbonaceous materials. So all of these have been achievable uh, through dedication of my research students, PhD students, postdocs, and so on, and also contribution from our industry partners from different areas and different departments and different companies. But to get into the topic of today, I mainly want to focus on the closed loop life cycle of FRP composites. I think every one of us familiar with what FRP is, fiber reinforced polymer composites, and the most likely everyone in this group know the advantages and benefits of these FRP composites. They are lightweight, high superior properties, mechanical properties, and also durability properties. And at the same time, they are lightweight. So they are perfect for lots of high-end applications. So this leads to when we are talking about high quality, high mechanical properties, but at the same time, high durability, but lower weight. So it's very fascinating, very interesting to industry to use it, and specifically for high-end products and reducing CO2 emissions from their uh, components, for example, in car industry or in aerospace. So we are always looking for a smaller materials. So the growth of these fibers, which in this research and in this webinar, I mainly focus on two major two major uh, fibers, carbon fibers and glass fibers. And we see the trend is always going up, increasing. And lots of industry are adopting these materials, and uh, from traditional industries to new industries, like, for example, hydrogen tanks and so on. So the high usage of these composites leads to high wastage. The wastage that we see is not just end-of-life components. It is also the waste materials that we see during manufacturing. So traditionally, we know that around 30% of those fibers and composites are wasted during manufacturing of the product. So that's a huge amount. And when we look at um, the energy consumption and for the production of these, for example, carbon fiber, and times it to these amount of waste, you see how much energy we are using, but we are throwing them away. So in terms of looking at, for example, one simple, one major sector, for example, renewable energy, which is one of the largest users of FRP composites. I love the turbine blade behind Jose. There was a turbine very nicely made. So the we see that the trend toward looking at and using and changing the attitude toward the renewable energy in different parts of the globe, that has led to the increased usage and production of turbine blades and installation of turbine blades. And we see this trend up to 2050. So that leads to waste material at the end. So if you look at, for example, a turbine blade, and if we cut it into different sections, so one of the main components is foundation. Reinforced concrete, nothing extraordinary. We are all familiar with that. We know how to recycle them. We know how to reuse them. The other part is the shaft, the tower, which is mostly made of steel, some part of aluminum and other materials. And most of them, they are recyclable. So if we look at these components, there is no issue. But if you look at that major component, which is the blade, you see that blade is made of different types of materials. It's one of them is fiber, is composite. So that you have combination of different polymeric materials, steel, balsa wood, aluminum, and so on, in to produce a blade in turbine blade. So if we look at those turbine blades, the size dictates the what sort of materials we have to use. Is it carbon? Is it the glass? Is it a combination of them? Is it hybrid system or not? So that 40 to 50% of this blade is made of that composite. And recycling of this is extremely difficult. And we know why, most of us, we know why that is difficult. When you cure the composite, separating that fiber from the epoxy is extremely difficult and energy intensive. So, so what can we do for that? How can we resolve this issue? First of all, if you look at waste treatment hierarchy, we see that the top um, performing treatment methods are first prevention, preventing a structure to fail and keep reusing the material or a structure in the current system, and then repurposing that. These are the greenest way of dealing with the structures and materials. And then when we don't have other options, then we look at the recycling. So recycling is not the first option. So that's what I'm trying to emphasize in this in most of my talks. My research and my work is related to recycling, but as I mentioned, it shouldn't be the first priority. You might be familiar with these techniques. Existing recycling pathways. We have techniques like co-processing, uh, mechanical grinding, pyrolysis, solvolysis, electrical recycling, and gasification, and other techniques. And most of the top ones, if we look at, for example, these top ones, we see pyrolysis, the technology readiness level is quite high. So they are already applied within industry, and we see recycled materials coming from pyrolysis plants. Mechanical recycling also very high advance. It's basically grinding them and recycle them and repurpose them, and co-processing for during the cement kiln within the cement kiln reactor, and other techniques like solvolysis, which is kind of chemical recycling method. So, but if we look at that and we look at all these recycling methods, the biggest challenge exists that when we have virgin composites, you're basically dealing with very well aligned fibers, nicely continuous and perfect condition. But when we do recycling, you deal with such kind of a scenario. So you have short fibers, you have randomly distributed or mostly entangled fibers. So how do you deal with that? And if we look at the performance of these aligned fibers and randomly distributed short fibers, you see the performance of those randomly distributed, it's very minimal compared to virgin aligned fibers. So there are a lot of challenges in this space. Um, one of them is that alignment, is the short nature of these recycled fibers. The other issues that we might see within industry and in practical application is transportation. For example, when you do deal with recycling of turbine blades, they are 20-meter, 50-meter, 100-meter blades. So how do we transport these? So logistics, WHS, how we can cut them, crush them safely to make sure that harmful materials doesn't get into our lungs, and so on. So all of these create challenges for us, but also at the same time opportunities. I think at the moment, for example, in terms of regulator framework, for example, in Australia, we don't have that regulation that still, for example, companies can dump their waste materials inside landfill, these composites. But I think in Europe, they have regulations that you have to deal with that and recycle it or reuse it, not sending that to landfill. So these regulatory frameworks are also very important. Or if you want to repurpose those turbine blades to use in other types of structures, who will certify those? So all of these challenges exist, but it creates opportunities, multidisciplinary opportunities for us to do research, which I see a lot of people here are doing very fascinating work, very interesting work in this space. I now look at some of the works that we did in the past, and we basically started this type of research in 2019, and we started we had this uh, we knew that there are existing methods, and we wanted to see which one would be suitable to look at and how we can proceed with those techniques, and which one we have to better to select. So we started with cost benefit and life cycle analysis, which helped us a lot because we could select those methods that are suitable for us and for the type of waste that we were dealing with. We looked at both CFRP and GFRP, carbon FRP and glass FRP, and because the scenario is different, the recycling method would be different for carbon and glass composite. Glass composite is GFRP is quite cheap, and you can't use energy intensive or very expensive methods for these recycling these glass fiber from GFRP. But for CFR, it makes sense because it is a strategic material, it is expensive, and production of virgin carbon fiber is very energy intensive. So it makes sense to use pyrolysis or solvolysis process for extracting carbon fiber from FRP. So we looked at these methods. We looked at uh, cost benefit to cost ratio, and also global warming potential of different methods, including landfill, incineration, mechanical, catalytic pyrolysis, solvolysis, and so on. So amongst these, for the type of our FRP composites, we looked at basically, we started with pyrolysis and oxidation method. And uh, if you are not familiar with those methods, pyrolysis is basically uh, uh, pyrolyzing or burning your samples within an inert atmosphere, in this case was nitrogen, and then extracting fiber and separating fiber from epoxy within that system. And then also reusing those epoxies as combustible gases or byproducts in after the process. So with that, we had these CFRP composites, and then after recycling, we could get clean carbon fiber from the composites, and very good quality, high quality, around 80% of tensile strength retention and 88% of tensile modulus retention, which is quite reasonable, the amount, and very good quality with minimum energy usage. So, but the challenge was that if you look at that in more detail, you see some discontinuity on the surface of carbon fiber that relates mainly to the temperature that we use. So we tried to optimize that, but after certain temperature, carbon fiber will get damaged. So we took that further. We worked with two different industries. One of them was is active in aerospace, and they produce airplane components. Another company was active in uh, 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 maintaining high-end sport cars, bikes, carbon bikes. So we got the materials from them, and we were one of the first teams that we looked at hybridizing the system, solvolysis process and pyrolysis process. Basically, we use solvolysis as a pre-treatment method for separating separating fiber from epoxy, and then go through the pyrolysis. What it does, it basically reduces the energy demand, reduces the amount of heat that we have to um, um, expose our fibers to. So by that process, we could see very good, high quality carbon fiber at the end, and that's shown on uh, the tensile test that we did in terms of tensile strength and tensile modulus, which was around 94% tensile modulus retention. So it was very good performance. But now, more recently, we are looking at other options, which I think we are the only research group that we are focusing on microbial hydrolysis. Um, this is effectively applied to those cheap materials like GFRP composites. It's very suitable for that. Basically, we work with fungi and three different fungi, and we do the microbial hydrolysis process, and we culture those spores and fungi and expose the composite to that, and they basically try to uh, use the epoxy as the feedstock, and then we extract the fiber. And we are looking at how we can improve the enzymatic performance and activities within those pore solutions. So this is ongoing research. We have a patent for that, and we are hoping that we can get into the publication very soon, get it published. But still, this issue exists. Still, we are dealing with randomly distributed, basically short fibers. How do we do that? We also looked at that in one of my PhD students, previous PhD student, she looked at basically different methods. You might know these methods for aligning the fibers. Um, uh, she looked at the systematic analysis of these realignment methods and how effective they are and how they can help us. And then we came up with our own technique to basically align these randomly distributed fiber and align them into the direction that we desire. So we developed the hydrodynamic alignment method, the HFAM method that we have, and we could get up to around 80%, 75% fiber alignment with our technique. And if we look at the non-woven format of our technique comparing to continuous virgin fiber, obviously that's far lower, but we expected that. We never can achieve the continuous virgin fiber, but that is something between aluminium and structural steel. So that is quite reasonable. And if you consider this is T300 carbon fiber, and if we have T700, so you can see that the mechanical properties is getting very close to a steel. So it is quite competitive. So we have the patent and a patent for the PCT patent on this technique, and we are working on applying these into different structures, different research areas. But the rest of my talk is mainly looking at cementitious materials, and we know that built environment contributing hugely to CO2 emission, and within that, cement production is roughly around 7 to 8% responsible for 7 to 8% of CO2 emissions globally. So it is very important to address that, and there have been a lot of research in this space. We also looked at started with literature review on existing methods for specifically for glass fiber and GFRP composite in cementitious composite, and compared how these different methods, mechanical, or catalytic pyrolysis or fluidized bed and so on perform. So mechanical recycling was one of the top performing in terms of the cost benefit, in terms of the total investment and global warming um, potential. So we focused with one of my PhD students. She is graduating very soon. Um, we started working on three aspects of it. And basically, we started off with looking at how these FRP waste, when we incorporate it into cementitious material, how these perform, and what would be the durability, performance of the mechanical properties, and so on. But at the same time, we have issues related to fiber dispersion, so how we can improve that performance. Um, but also, when we are talking about carbon fiber and cementitious composites, this is very tempting always because they are conductive materials. So they have sensing properties. They have electrical properties. So self-sensing and using them as a sensor in concrete is also tempting. So that's why we looked at these three major aspects. But to start, we worked with two different companies. One of them, as I said, was active in aerospace industry, airplane components, and another one was in construction, and they were producing cross arms out of GFRP. So what we did, we downsized these GFRP and CFRP components, and we pulverize them, we convert them to powders, and then we replace cement uh, based on these CFRP and GFRP recycled material. And consistently, I think a lot of people have been done this kind of research. Consistently, the properties of these materials were better than the control without any uh, um, waste materials. The performance was better than the controlled. In terms of mechanical flow table, mechanical properties, compressive strength, and shrinkage, dramatically reduces shrinkage, and that's because of the fibers inside the composite. And obviously tensile strength, because we have fiber, obviously the tensile strength increases, and flexural strength. The same thing happens to resistivity when, conductivity. When you use CFRP, you basically increasing your conductivity. Carbon fiber is very good conductive materials, and then water absorption reduces, and that's due to the reduction in void inside the concrete. So you see that a lot of properties improved by using these recycled materials simply with minimum energy to replace cement within the concrete. And if we look at for example, CSH and hydration product around these fibers inside concrete, you see that they are basically forming around fibers and create a good bonding. The other work that we did was focusing on those offcuts that we mentioned. 30% are wasted during the manufacturing process. A lot of fiber offcuts are wasted during the process. So how do we deal with this? Basically, it's addition of fiber inside into concrete. But when we do that, we have to be very careful, because addition of fiber is good, improves the tensile strength, flexural strength, and possibly shrinkage, reduces shrinkage. But at the same time, it leads to formation of voids and increases the void and permeability of the concrete. And that's why we looked at how we can characterize that, because we looked at with microcity and to analyze voids and also carbon fiber inside the cementitious material. And interestingly, we realized that by addition of that carbon fiber, you see some specific type of specific shape of void forms inside the cementitious material, and those elongated voids leads to higher permeability and lower mechanical properties. So it is quite interesting to see those kind of performance, the shape of void and relationship between the shape and also uh, carbon fiber and dosages of carbon fiber inside the cementitious material. But the second part of our work, as I said, that dispersion is extremely important and critical. So how can we improve that dispersion? Um, why dispersion is and dispersion is important? Why surface modification is important? Because basically that interaction between fiber and cementitious material is through that interfacial transition zone. And if that transfer of the load is happening between that ITZ, if we have a very strong, robust ITZ, you have very good performance from your cementitious material. So how can we improve that? There are different techniques. For example, electrostatic attraction through electrostatic attraction and ion bonding, or chemical bonding, which is very strong bonding through functional groups and CSH gel in cementitious material, and or it could be mechanical interlocking or the combination of these. So um, based on that, there are different methods. They have advantages, disadvantages, obviously, but selection of those appropriate method is a fine balance. And you have to look at performance, cost, environmental, and sustainability of those methods, and so on. So with my PhD student, we looked at basically bio-based carbon fiber surface modification. And why we selected that? Because usually construction industry is a conservative industry and doesn't want to deal with very harsh chemicals and materials. So these bio-based um, uh, materials, which was tannic acid and citric acid, very weak acids, we use them to functionalize the surface of our carbon fiber uh, and improve the performance. We basically desized our carbon fiber first, and then we exposed them to tannic acid or oxidation and citric acid, and then we functionalized the surface with hydroxyl group, and then we try to incorporate them into cementitious material. And when we look at atomic AFM images, we see the surface topology of these carbon fiber and roughness of that. So you see that we are improving the roughness of the surface. We also incorporating functional group on the surface. So that increases the bonding between fiber and the cementitious material and improving the ITZ performance. So that's basically very successful, and I think it is quite scalable within the industry and very simple process that can be achieved with normal facilities that we might have. But if we want more high-end, I can say, composites and surface modification, for example, and in situ surface modification during the production of carbon fiber. So obviously, electrochemical grafting is one of the good options. And we again work with on those hydroxyl and amine groups to functionalize those on the surface of carbon fiber and then see how that performs. We looked at interfacial response between when we pull the fiber from the surface, as you can see from the concrete, and then identify the interface and pull out force and so on. So it was quite successful, and we saw that mostly hydroxyl group are doing better than amino-functionalized carbon fiber. And that was probably because of the hydration products and interaction between hydration products and these uh, uh, functional groups on the fiber surface. And you can see this is simple carbon fiber, virgin carbon fiber without functionalization. But these are the functionalized carbon fiber. You see the interaction of CSH and carbon fiber, how well these are basically bonded to cementitious material. But the final area that we looked at was basically using that electrochemical performance of these materials when we incorporate carbon fiber, for example, or inside concrete. One of the things that is we always look at, for example, mechanical properties or some of the durability properties of these concrete when with waste materials, but specifically for the case of carbon fiber and CFRP in concrete, we need to be very careful about corrosion, because usually to avoid corrosion, you need high resistivity inside concrete. But when you add carbon fiber, carbon-based material into your cementitious material, you're reducing the resistivity. So you are increasing potential for corrosion happening. So that's why we did this research. We looked at how the corrosion performance of the, we can measure them and how they perform. And we basically looked at, we saw that obviously the corrosion potential of those recycled carbon fiber, this is the reference without any, that's pure cementitious material. This is the cementitious material with virgin carbon fiber, recycled carbon fiber, and recycled CFRP. So out of all these, that the one with recycled CFRP performed very well and had lowest corrosion within all those and very comparable to reference. And the reason was that it's true that we are adding a steel carbon fiber, but that epoxy part of the CFRP helped to basically improve resistivity as well as filling the gaps within the voids. So that improved the durability properties and water, reduce water ingress inside our concrete. So that these are the things that we need to consider when we are dealing with incorporation of these materials in concrete. But in terms of that self-sensing that we were talking about, again, we did these piezoresistivity tests, and we looked at when we incorporate these composites into concrete, both in terms of CFRP and carbon fiber, and also GFRP, how they perform, and if we can use how they respond. And we did dynamic testing and incorporate these concrete into those samples and tested them, and we found out that the response of those samples with carbon fiber in them and recycled carbon fiber, the response wasn't really stable. So it wasn't very good for self-sensing. Piezoresistivity wasn't stable. But those with CFRP basically had a better performance, a kind of continuous and stable performance. That's something that we can manipulate and get self-sensing performance out of them. So that is probably due to the agglomeration of fiber inside concrete or alignment of fiber inside concrete. But with CFRP powder inside concrete, I think that the dispersion is better. You have condenser samples, so you have better networking of electrons and conductive materials inside your cementitious material. So I don't know how much time I have, but I just couple of case studies related to these waste materials. We teamed up with transport authorities here, road authorities in New South Wales. We know that Australia has a long shoreline, and obviously when we have exposure to marine environment, we have corrosion. That's inevitable. And one of the techniques that is very common for mitigating those corrosion and infrastructure failure is basically cathodic protection, or in this case, impressed current cathodic protection. So the challenge that our industry partner had was they applied these ICCP or cathodic protection system onto their bridges, but the system, how it works, it's basically that's reinforcement, and they embed a impressed current anode into the surface, and then they embed it within the concrete. And what it does, it takes the chloride ions away from steel reinforcement and take it out of the system. So it's basically, instead of chloride ion exchange ions with reinforcement, they try to avoid that, and they impress the system within that environment. So, but with the challenge that they had was acidification of the mortar on those anodes. You can see this is a mesh anode on under the mortar, but after a while this is acidified, and then that washed away and the whole system failed. So they spent a lot of millions of dollars on one bridge, for example, to install these, but after a couple of years they washed away, they failed. So they asked us how we can improve these. One aspect was improving acid resistant of these material, these mortar. We looked at geopolymer concrete, and we are still working on that and improving that. But
Sorry, Ali, can you hear
conductivity,
me?
yes.
Sorry, sorry to interrupt you. Could you please wrap up quickly in 5 minutes
Yeah,
so
yeah,
that
yeah,
we
sure.
can
It's
leave some time for
I'm at the
questions?
end, yes.
Yeah, thank you. Thank you.
So the conductivity is extremely important in this case, because you are doing ionic conductivity between the environment and electronic conductivity. So now we are using these recycled carbon fiber within these mortar to improve the conductivity and install it onto a bridge for cathodic protection. So the other type of applications that you can see and we have been doing within the group was incorporation of carbon fiber or glass fiber inside uh, filaments for 3D printing. So that's one of the other areas of the research that we're doing. And improving, basically using face masks or polypropylene from different waste materials, and incorporate carbon fiber into it, make filaments, and then 3D print different components and materials out of them. So it's basically more toward upcycling of these CFRP waste. There have been research on uh, basically developing bio-based thermoset polymers, which is really nice, very interesting work, and that might even resolve a lot of issues related to dealing with waste materials, or repurposing. So these are all those techniques and methods that have been established, have been worked. But coming to the summary of my talk is basically prevention, reuse, and repurposing are the priorities. And then looking at those logistical issues, basically regulatory frameworks, and who deals with the waste, who deals with the end of products, end of life products, and so on. So this is very interesting, exciting area, and I would love to hear your thoughts, and would happy to answer any questions if there is. And I am always happy to collaborate with anyone. If any part of our research of interest, please let me know, and I'm more than happy to work with any of you guys.